Hello and welcome to another video. In this video we're going to be doing peak index in a mountain array. And in this problem you have a mountain, and essentially I'm not going to read the readme, I'm just going to explain it. I think it's going to be a little better, but essentially you have a mountain like this where you have one element that's above the rest. So you have an element like 8, and then you have at least one element on both sides that's smaller to make a valid mountain. So at least we will have like an element here, an element here. And this is essentially an array, so this would be like 6, 7, 8. But you can have as many elements as you want here, and as many elements as you want here. And then this is decreasing, and this is decreasing as well. So for our examples, let's go through those. So instead of this 8, we have a 1, and we have a 0 and a 0. And then our peak is up here. And we have another example where we have a 2, and we have a 1 and a 0. And by the way, so what they want you to do is return the index of this in the array. So this would be like index 0, index 1, index 2, index 3. So this 2 would be index 1 in this example. And the final example, we have a 10, a 0, a 5, and a 2. Okay. And so here this would be index 1, so we would return index 1. So we're guaranteed to be given a mountain array, right? So let's just make some like assumptions here. Like we're going to have some number, we're going to have some numbers here, you know, from 1 to n. We're going to have a number here, so this will be like 1 to n. This will be 1 to n. So let's make some assumptions, and we have an array, and this is some number n. So what assumptions can we make? We know that this is decreasing, right? We know that this is decreasing. So let's just draw an example. Let's just say we have an array, and we have like 10 up here, then we have like 8, 6, 6, 4, 2. Same thing here, 8, 6, 4, 2. So we know that for it to be a valid mountain array, there has to be at least one element on both sides. So when we can figure out our boundaries for the mountain array, by the way, this is also a logarithmic function. So for a logarithmic function, there's not too many functions you can use, but we're trying to get this in log n time. So we're going to use binary search. So for our left, we know we don't need the 0 index for the mountain array because that can never be like the mountain array. There has to be at least one element on both sides. So the left is just going to be index 1, and the right is going to be the length of the array. So let's just say length of the array minus 2, right? Because minus 1 is the last element. It can't be the last element. There needs to be one element on each side. Now, what I like to do in these binary search problems, I actually like to figure out something. What I like to do is I like to set a result equal to a value, and then we're going to try to maximize or minimize it. So you could do this one of two ways. But notice that this value is greater than the value after it. And so we can just look for all values that are greater than the value after it and find the leftmost value, right? So we're going to set the result equal to the right to start off. And we're just going to simply check. We're going to simply binary search, and we're going to look, we're over here. Is this value greater than the value after it? Yeah, it is. Okay, let's make that our peak. And let's keep doing that until we get the leftmost one, and the leftmost value than the value after it. So just say, we have some pivot is greater than pivot plus 1. And so the leftmost one of these is going to be our answer, right? You could do this the other way, where you could say, let's make it greater than the number before it, and then the rightmost one is going to be that answer. Yeah, well, either one of those is fine. Now, essentially, we can just have a binary search that goes through these, and if we find the number, we're just going to try to make this result the leftmost result possible. So at every single number, we're just going to say result equals, we're trying to minimize the index here, right? So we're going to say min of the result and the pivot. And so, for example, let's just go through how this would look essentially for this algorithm. Well, let's do like a dry run of it. So let's say we have 2, 4, 6, 8, 10, 8, 6, 4, 2. So we have this array, right? Our result is going to be, and let's index these as well. So this is index 0, 1, 2, 3, 4, 5, 6, 7, 8, And then let's get our result. So we're going to start our result by being right. So remember, in this array, our left is actually going to be something else. Let's use another color here. So let's have the left over here. Let's have the right over here, right? We're not going to start the last element because the last elements can't be the mountain. So we're going to say the result is index 7. And now we're simply going to get, let's just go through this binary search and how this would work. So we're going to get the middle element first. So, right, 1, 2, 3, 4, 5. So this middle element is going to be over here. This is going to be the first pivot value. So we're going to have a pivot here, and we're going to check, is the pivot greater than the value after it? Yes, it is. Okay, in that case, let's update our result to be the smaller number of pivot and the result. And so if the pivot is here, the pivot is 4, now our new result is going to be 4, right? And now that we got this pivot, the pivot was over here. I'm just going to mark the pivots down here to make it easier. Now we need to think, which way are we traversing, right? Like, we got some value, but remember, we can, if you look at this mountain, like, any one of these values is valid. Is a valid, that would pass that p is greater than p plus 1. So we want to be traversing as far left as possible. So we got this value here, but now we want to be traversing as far left as possible. So if our pivot was here, if we want to be traversing as far left as possible, we can make the right this. So we get rid of that. Now our array is here. And what's our new pivot? So our new pivot's over here. And now we check, is our pivot greater than the one after? No, it's not. Okay, well then we're not going to update our result. And so if the pivot is not greater, that means we're somewhere over here. And so let's say we're here. Where do we want to go? Well, we want to go to the right. So we want to go to the right. How do we go to the right? We're actually going to update our left to be pivot plus 1. Now we're over here. And now our pivot is finally this 8. Our left and our right are both this 8 value here. So then we need to say, is our pivot greater than pivot plus 1? No, it's not. Okay. And then since it's not, we're going to update our right to be, we're going to update our left, because remember, we're still like to the left. So we're going to update our left to be over here, and now our binary search condition is broken, right, where left is less than right. And our result is at index 4, which is the 10. That's how this algorithm is going to work, essentially. And I think this is a nicer way, this is a nicer template for doing binary search, as opposed to checking, the left and the right and trying to get the number early, because your time complexity is going to be the same. Like, it's going to be log of n even if you end early. So you don't actually need to make sure you find the target. You can just get rid of everything, and you're guaranteed to be, worst case log n. So now we have enough to code this up. So we're going to say we're going to have a left and a right. We're going to make this 1 and length of array minus 2, right? Because it can never be the 0 element. So now we could say, let's make the result equal to the right. We could say while left is less than or equal to right, say pivot equals left plus right, mon2. Now we can check our cases as we have here, right? So if pivot is greater than pivot plus 1, so if array pivot is greater than array pivot plus 1, what do? Well, we need to change our result. So result equals min result pivot. And then where do we need to go from our picture? If we're somewhere over here, so we need to go left. So to go left, how do we do that from a pivot? Pretty straightforward, right? Right equals, so it's going to be r equals pivot minus 1. Hopefully I did this right. Did get it the other way. Otherwise, we are on the left side, so we need to go right. So then it's left equals pivot plus 1. Let's fix these. Okay. So now that we went through this binary search, we just simply need to return the result. Pretty straightforward, and hopefully we don't have any mistakes. And it looks like we did. Looks like we have an infinite loop here. Let's just double check. Oh, so this left needs to be left. That's one thing. Okay, we do have some errors here. So it says we have 2, we expected 1. Okay, so there's another mistake here. So this needs to be index, not pivot plus 1, right? So that is also a mistake. All right, I'll submit that. Nice. And so, I mean, the time complexity for these should basically all be log n. And so, yeah, if you do end it early, you could do the checks. If you end it early, it'll run a little faster on LeetCode, but the actual time complexity is not going to matter. Plus, we save ourselves a ton of debugging for harder binary searches, because for this case, you can't be out of bounds, right? So you could have a check, but for a lot of them, like let's say you have something like this, you're actually going to be checking to the left and to the right, and then you might get a lot of out of bounds errors or a lot of edge cases, which you don't need to do. And it's not like we're writing a compiler here, so we don't need to maximize our completely maximize our efficiency as long as our big O is the same, right? Like we're not actually gaining anything super valuable, just running a little bit faster on LeetCode. Okay, so for this, the time is going to be log n, and the space is going to be O1 because we don't have any other variables here, right? We just have a left and a right and a result, so we don't have anything else. But yeah, I really like using this template, and you can use this if you want to avoid errors. Otherwise, you could, not use. I always prefer to make my logic where it's less than or equal to, and then I just run out of all possible options and store a result. There's other ways of doing this where you could say like this, and then you have checks in the end and so on. So it's just personal preference type of thing. But yeah, hopefully you liked this problem, and if you did, please like the video and subscribe to the channel, and I'll see you in the next one. Thanks for watching.